We've got a probability distribution question here, and the distribution is defined as shown. It only occurs, well, non-zero probabilities for 2, 3, 4, and 5. We're asked to show that the probability that x equals 2 is 15 over 32. To be honest, this is like a nice question to kind of just to get us going. Okay, it's only 1 mark, just to make sure we can use the formula. So I'm going to get x equals 2 equals 15 over 64 times 2 squared over 2 factorial, which is just 2. That ends up being 15 over 64 times 2. I guess because I could show that question, I should probably just, yeah, write that step down. And that's going to give me 15 over 32. Part B, given that x1 plus x2 plus x3, when we're finding 3 independent observations, equals 9, determine the probability that at least one of these 3 values is equal to 2. So I'm going to write this down using a probability. It's a probability that a value s equals 2, given x1 plus x2 plus x3 equals 9. So we can now use the fact that the probability that A given B, that is equal to the probability of A and B over the probability of B, because this is, we're like basically using a reduced sample space. This is, I'm not going to go into any more details in this formula. It is given in the formula book, but it's basically, we're not dividing by the whole kind of 1 anymore, because, we're only allowed to have B occurring. So we kind of scale the probability using that. So for us, it's going to be the probability that the value or values equal to and x1 plus x2 plus x3 equals 9 divided by the probability that sum is 9. All right, the first thing to do is going to be to write this distribution down, but a little bit like in a table. So we've either got 2, 3, 4, or 5. Now we've just worked out the 15 over 32 for 2. And you can just continue to sub in for the rest. I'll just do the first one and I'm going to quote the rest of them. So it'd be 15 over 64 multiplied by 2 to the power 3 over 3 factorial, which gives 5 over 16. And if you do the other two, you should get 5 over 32 and then 1 over 16. And by the way, a little check will be to sum these up and check that you get 1, and you will. So let's work out the probability that the sum is 9. So I've got to think about all the different ways that I could get a sum of 9. Well, let's start with the largest value, 5. Now, if I had 5 and another 5, it'd be too big. If I had 5 and a 4, it'd be too big. If I had 5 and a 3, I'd need a 1, which I don't have, so that's also too big. The only way I can get 9 after I've got a 5 is to get a 2 and another 2. And of course, we could reorder this. We could get 2, 5, 2, but we'll deal with that in a minute. I'm just sort of saying those 3 numbers in some order would get us a sum of 9. So what if I had a 4 in the mix instead? Well, 4, I can't have another 4, but I could have 4, 3, 2. And actually, that's the only way that I can do it with a 4 in. What if I don't have a 5 or a 4? I could have all 3s. So these are different ways that I could use 3 numbers to get a sum of 9. Just got to think about the permutations as well, and then we can work out the probabilities. But let me deal with the 5, 2, 2 in that specific order. It'd be 1 over 16 times 15 over 32 squared. But I could put the 5 in the middle or on the right. So there's actually 3 ways that I could do this. Because 5, 2, 2, 2, 5, 2, 2, 2, 5. I can just times by 3. Alternatively, you can say there's 3 objects, 2 identical, 1 the same. It's 3 factorial over 2 factorial, 1 factorial, which is 3C1. Okay, that would also get you 3. I'm just kind of explaining it in a different way. For 432, we're going to get 5 over 32 times 5 over 16 times 15 over 32. We've just got to think about the orderings. Now there's 3 objects now. There's actually 3 factorial ways of arranging 3 objects, 3 times 2 or 6 ways. Okay, you don't need to write them all down, but it's just, yeah, that's it, 3 factorial. I will write some down. So if I had A, B, C, you do A, C, B. We could then put B at the front and get B, A, C, B, C, A, C, A, B, and C, B, A. And I've systematically written them all down. That's where the 6 or 3 factorial comes from. There's other ideas as well to fully justify. But n objects have n factorial ways of arranging them. Then 333. This is just 5 over 16 cubed, and actually there's only one way to have that. I can't swap these around, it'd be the same thing. So I'm going to write down what each of these is. Okay, and this is something I've done earlier. So we get 675 over, I kept it exact as fractions, and then 1125 over 8192, and 125 over 4096. So back to my probability. Well, actually, I did work out the sum. I thought, yeah, it's good to work out the sum. So that ends up being 3. It looks a bit confusing. It looks like I'm dividing there. So, okay, I'm just going to write down probability x1 plus x2 plus x3 is therefore going to be the sum of these, which is 3425 over 16384. So now back to our main probability, this one. It's then going to be, well, I'm interested in when I get the sum of 9, but I get at least a value of 2. And that's going to be these two added together. It's everything apart from the 333. So if you add those two up, you actually get 2925 over 16384. And now we just have to divide by that other thing that we've just found. Okay, and these have the same denominator, so you can actually just cancel them out and get 2925 over 3425, which ends up becoming 117 over 137. And that is our answer. That is the probability. Okay, if you want to write it to 3 significant figures, actually that's completely fine. It'd be about 85%. Finally, we're asked to determine the probability that she chooses exactly 10 values of x when she chooses values at random until she's obtained x equals 2 3 times. Okay, this is the last question. It's testing us. So we are picking, well, we're picking until we get 3 values, but we're looking for when she chooses exactly 10 values. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So for this to happen, we must pick the last one as being a 2. Okay, that is fixed. But then there's lots of different ways that she can pick values to get x equals 2, 3, another 2 times. So could get a 2 here and maybe a 5 here and maybe a 2 here and a 4 here and so on, like absolutely loads of ways. Now that is not a good way to do it. So we don't really care if she gets a 2 or gets a 5 or a 3. We just care that she doesn't get a 2. So I'm going to write capital N for not getting a 2. And then maybe she gets a 2 there. So actually I'm looking at arranging these. I've got 9 values that I'm allowed to arrange, but 2 of them are the same and another 7 of them are the same. And this is where our other aspect of permutation comes in. It's going to be 9 choose 2 for all the different arrangements. And where this comes from, I'm running out of space here, but as I was talking about earlier, there's n factorial ways of arranging n objects. So there's 9 factorial ways of arranging 9 objects. But when some of them are identical, every time I get an arrangement and I swap the 2's around, it would be the same. So I need to divide by 2, or 2 factorial, or just 2 in this case. But then actually I can swap the n's around as well, and there's like 7 n's. I can actually arrange every single permutation I have. I could swap the n's around and it would look the same, and there'd be 7 factorial ways in which I could swap the n's around. So I also need to divide by that. And that's just something you always do. Like if you want to say how many ways can I arrange the letters in the word banana, it would be 6 factorial for the number of letters. We would divide by 2 factorial because there's 2 n's. Then we would divide by 3 factorial because there's 3 a's. You don't need to divide by, well, you can divide by 1 factorial for the b, but that doesn't do anything. So this is like an even deeper result, but we just need to know about this in this situation. So that's my 9C2 ways of arranging. Okay, but now I'm going to actually work out the probability of getting 2 2's. Like forget the order. It's like I did here, but before I did that, the probability first, and then I did the arrangements. I did the arrangements first here, but it's going to be 15 over 32 squared to get 2 2's. Like I'm saying that I'm going to get 2 and then a 2, and then I'm going to get 7 n's in a row. That's kind of what I'm saying. So to not get a 2 is just going to be 1 minus 15 over 32. That's 17 over 32. And this is to the power of 7. So this by itself is just me getting 2 2's followed by 7 not 2's. But that's when I need to think about the arrangements because there's all these other ways I can do it. And that's what I'll get. Okay, I've just got one other bit to do, and that is I need to get a 2 at the very end. So I have to times by that probability as well. It's fixed, but I still need to find out the probability. So I times by 15 over 32 one more time. I think it's really good to just like stick it at the end and then focus on the other 9 rather than trying to get it involved. Just, we're basically looking for if we have 9 objects and 2 of them are 2's and 7 of them are not 2's, how can we find the probability of that? And then, all right, the 10th one has to be a 2, so we'll times by that probability as well. And that is our answer. When you work it out, I think your calculator just gives a decimal. It did for me. So 0.044281, which rounds to 0.0443. Okay, so proper test on whether you understand the binomial distribution, the ins and outs. So if you're a bit confused by that, all I can say is like, look into it more, get some more questions, talk about it, get your head around it, because it's a really interesting topic that only just gets touched upon, like in this very final question. But it's kind of at the heart of, lots of maths and useful maths, in fact. Think about um, different hands in poker. It all kind of has these ideas underpinning it, because there's different ways that you can get your flush or whatever, your straight. Anyway, we're not doing that here. We're dealing with this question, but this is our answer, 0.0443. Thanks for watching, and hopefully it makes sense. Well done.